Okay, so we're very happy to have Matthew Yu from Oxford, who will tell us about the non-semi-simple non-reversible symmetry today.
Well, thank you for having me here. It's a great pleasure to be at the Institute. This is my first time ever coming here. I want to talk about some recent work I put out with my collaborators, Clement Delcamp and Heng from IAS. So I work in the field of categorical symmetries, non-invertible symmetries, but recently, much recent activity, especially kind of focused in the condensed matter setting, even in the high energy setting, has focused on fusion category symmetries. And so while fusion categories do represent, a good number of categories that we can actually get our hands on and work with, and they're very nice for constructions and things like that. As a mathematician, if handed a fusion category, you would think to yourself, why do I care about fusion categories? Because the general category you can have in your mind is particular not fusion. You can have actually very wild things. So kind of my goal today is to understand, so the goal is to understand kind of what happens, what about more general categories. By that, I really want to go beyond fusion. Okay, so and also, unpacking these categories, I also want to see sort of what are the physical applications. Physical.
So go beyond means that we hold fewer restrictions or more restrictions.
I relax things. I relax things. So I have more categories now. I'll tell you exactly those things today. But really, sort of the kind of the word of the day is non-semi-simple, and I'm going to be focused on kind of 1 + 1 dimensions. So we focus on a finite non-semi-simple category in 1 + 1. So just like in Sesame Street, today's talk is brought to you by the words non-semi-simple and the neighbor 1 + 1. And the running example that we'll have in mind is a particularly nice category. It's going to be the module categories of something called the Taft algebra of dimension 4. Some people might also call this the suite of 4 algebra. It goes by different names. And really, the reason why I really want to focus on this running example today, this is also what the paper talks about, is because this is sort of like one of the simplest, really finite, non-semi-simple things that goes beyond the fusion example. And it's workable, kind of nice, but there are some interesting implications of this. So my goals for today, let's go with this.
What's the addition on the algebra process that was semi-simple?
So I'll unpack the algebra for you in a little bit more detail, but this category is a non-semi-simple category, whatever that means. But I'll
what's the general condition on the algebra process that this representation category is semi-simple?
So the general condition, there could be many conditions. In particular, this algebra has a nilpotent element. There's something that squares to 0. So to be non-invertible, there's many different ways to be non-invertible. In particular, squaring to 0 is a way of being non-invertible.
Non-semi-simple.
So non-invertible is one thing, but this non-invertibleness implies non-semi-simplicity of the category. It's an algebra with an element that's non-invertible as an element of the associative algebra, for which when you take the category of, this becomes non-semi-simple, whatever that means, which I'll unpack. Okay, so my goals for today. So the goals of really kind of unpack some mathematically interesting facts, mathematically pictures of such a non-semi-simple category, I should really stress that like there's some quite interesting mathematical features already in just this category. And we want to see kind of, we want to give them physical meaning. Which we can do. First goal. The second goal is sort of a thing that we should always be looking for, which is there anything already? Anything already that has secretly, or maybe can be described by a non-semisimple symmetry, and really sort of is using this example like a better way of framing such a thing. So these are the two things I'll be talking about today. Does this go upward? I'm really forcing this. Does it go up?
It goes up with effort.
Okay. Okay, so before I go into the non-semisimple stuff, let's get everyone on the same page. I just want to kind of do some kind of quick background on semisimple 1 categories. And this will sort of be all the technical stuff that I really need. So I'll put some definitions over here. I'll get rid of them, and then I will document information about the algebra on this board, and then lift it up there so we can have it for the rest of the talk. Okay. So definition, the things that probably most people are familiar with, but I'll go through them anyways. Object X is simple enough if one of the following equivalent conditions hold. The first is every sub-object A inside X, is either 0 or an equivalence. Number 2 is X is indecomposable under direct sums, and kind of the word indecomposable is a word that kind of representation theorists like to use a lot. I'll also use this in the talk. And another way of thinking about it is kind of endomorphisms of X is just C, or like the graph field. And kind of, you all know this very well from just regular good old Chern-Simons theories. And a way of thinking about this is that kind of, if you just take an object in Chern-Simons theories, there are no non-trivial endomorphisms of objects, just like scaling the object.
So let's see, you're not assuming it's a tensor category? Or are you?
I'm assuming it's a tensor category.
You are?
So yes, X is just a
category, and it's a tensor category.
yes, X is just an object in one of those, but tensor.
It's a tensor, okay,
Yeah.
okay, good. And sub-object just means there's a morphism from A into X or
Yes.
more?
That's right.
That's all.
That's just a morphism.
And for the non-experts, what's the distinction between tensor and fusion?
I'll get to there. I'll get there in just a moment. Well, I'll spell out the fusion and I'll tell you exactly what's relaxed. So this is just kind of this is really to define the word simple, and then kind of I'll go into the next thing, which is semi-simple.
So this is for simple objects, not simple categories.
That's right. It's a simple object. Object of X is called simple. I'm defining for you what a simple object is. You should have in mind that, as Greg says, this lives in something called a tensor category. But for right, that's the most general sense I want to talk about. Now I'll tell you about fusion categories. We'll go kind of beyond fusion categories. Actually, I have a lot of space here. So, right, definition: a semi-simple 1 category. C satisfies following. So let me just as a kind of a notational thing, semi-simple here, you could also take this as kind of fusion category, kind of what I was saying above there. And semi-simple categories, there's lots of cool theories about there. We understand kind of higher semi-simple categories as well, fusion 2 categories, a little bit of fusion 3 categories and things like that people have also worked on in this room. And kind of the generalized fusion categories is really like the tensor category. So the semi-simple category has the following thing. So objects are direct sums of finitely many simple objects. We know what a simple object is now. It's Karoubi complete. Maybe some people like condensation complete. Get that. And 3, the Hams of xi, xj is equal to delta ij on the simples. Okay. So this is the definition of a semi-simple category. These are kind of things that we've all been working with for a long time in this community. We've constructed lots of examples of them, seen them. So
1, 2, 3 are equivalent or
satisfies the following conditions. You need
all 3 of these?
Yeah.
Okay.
Yeah.
Okay, then could you say what Karoubi completeness means?
So yeah, there's kind of many ways. There's kind of many ways for me to say this, but sort of maybe the more intuitive way of saying such a thing.
Don't use the C word.
Right. So the idea of using this Karoubi completion is saying that kind of I might have other objects inside my category that are not given by the simple objects, and then there's a way of kind of almost kind of Cauchy completing my category to get all the other objects of them, not as direct sums, but sort of kind of you should be able to build these objects in some other ways using the simple objects of the categories. I want to say condensation, but you told me I'm not allowed to say that word.
I'll be more liberal. I'll allow you to use this word if you told us what it means. But I'm not that much more liberal.
So I can unpack this thing in another talk, but this is just for completeness of the talk. This is not going to be
This is
important.
not important for
This is not going to be important for everything else I'm going to say. But if you want a more detailed kind of
Does it make
conversation.
sense kind of in more lowbrow way that the simple objects generate everything?
That's right. In a semi-simple category, this is the case. That's right.
Okay, so how much beyond what I just said, how much of this blockwood do I need?
So sorry, how much of this do you need for the rest of the talk? You need the following thing. You need the definition of what a simple object is, and you need to know that all the other objects are direct sums of the simple objects. What I'm going to show you is I'm going to give you an object that's not a direct sum of simple objects. Think of it this way. So I'm just going to spoil a little bit of the talk, but since you asked, you know that there are certain sequences that look like such a thing. There are certain exact sequences. And if an exact sequence splits like this, then B is a direct sum of kind of A and C. Or you could think of B as an object, it's an extension of kind of other objects. And, in a semi-simple sense, all sort of sequences in my category split like such a thing, such that B is an object, but it's a direct sum of finally many simple objects. But this is not always the case, and such sequences don't have to split. And in this case, B is not decomposable as a direct sum of things. So it's just an exact sequence. Instead of another set, so I'll tell you why this is a generalization. You can think about kind of matrices and diagonalizable matrices. To be able to diagonalize a matrix is a very strict condition, right? But matrices can be Jordan block diagonalized. You should really think of this non-semisimplicity as kind of like a Jordan block type of decomposition, I think. And that's of course very, very much more general. So kind of maybe the way I'm saying this is sort of we've been working, and the community has been working a lot towards kind of like diagonalizable like categories, but like really you can go far beyond that. But I'm always in the finite sense. Always have finitely many objects. Does that answer the question? So since this is some background, and let me unpack the structure of the algebra. the Taft algebra. I'm going to collect all the data inside of one board. So if I see if I can do that. So as an associative algebra, it's given by the following thing. You pick C, you have two generators with the following relations. Squared is equal to 0, g squared is equal to 1, g is equal to minus gx. Okay. And then immediately from this, I'll just write down the representation category. So I can give you the objects. This one. Now let me start off with the simple objects. The simple objects are given.
Is it a four-dimensional object?
It's a four-dimensional
What are
object.
these?
So it's given by 1 xg xt.
What is H then?
Oh, I'm so sorry. This is x. So simple objects, let me denote them as 0 and x1. Just the simple object is just a one-dimensional thing. So call this W1, call this V1, such that I need to tell you the action of the objects. I need to tell you the action of the algebra on this basis. W1 is equal to 0. G W1 is equal to W1, so eigenvalue 1. And then x V1 is equal to 0. G V1 is equal to minus V1. Okay. And then now I want to introduce for you the projective objects. So I've run myself out of room. These are what I call the projective objects.
S0 and S1? The two one-dimensional
They're
representations.
two one-dimensional representations. I'm calling them simple objects.
And there is no two-dimension.
There will be.
Okay.
Yeah.
Representation in terms of Pauli matrices, right?
So
Plus and sigma 3.
So that's basically right. And yes, that's basically right. I'll tell you why this is correct. There's a way of representing them as Pauli matrices because this category has a fiber functor to the category of vector spaces. And then there's a way of kind of really, I can kind of write the elements of this category, the objects of the category, I can express them as kind of like 2x2 matrices, which is what I'll do. And later on, you'll kind of see that here. But that's exactly your point. Not all categories you can do this with. Because this is a representation category of a Hopf algebra, you always have fiber functors, but in general, this is not the case. So the projective objects, there's also two guys, P0 and P1. So this is a two-dimensional thing. B0, 1, C of W0, B1. And let me just draw for you what these guys look like. So let's start with V0, V1. This action is by X. And I'll draw for you the actions by G over here. So this is -1, and this is 1. These are the actions by G, this is the action by X. Notice this is truly like a two-dimensional thing, right? And it doesn't split because this X is nilpotent, so I can't go back. So this is really kind of the object P1, like spelled out.
So X takes V1 to 0.
That's right, it takes P1 to 0. The other guy is basically the same thing.
And where these -1s, that's the action of G.
That's the action of G. Yeah. Same thing again here. The action of X, and then -1. Okay. So crucially enough, you see, since and you can kind of think of this the same way, but sort of X acts trivially, and it's kind of just
So those are the two representations that Tom just mentioned.
sorry.
Those are the two representations that Tom just mentioned.
Yeah, so kind of there's these guys and there's these guys. These guys reflect sort of a Z, kind of like a rep Z2 fusion. And the reason why is because there's something else about the Taft algebra that I didn't quite tell you about, but you can see that there's kind of like a hidden Z2 inside here. Like a CZ2, the group algebra of Z2. It's in particular like a Hopf algebra, actually. This is just the associative algebra. So there's in particular a CZ2 hidden inside here, and that's exactly sort of, you can think of it as kind of like a Pauli X or something. And this is going a little bit more, but you see, Because of the nilpotent nature, like Pauli X is not gonna do, right? We really need kind of a matrix that's sort of like one of interest or something like that. And you'll see this a little bit later when I construct it. So
I didn't understand what you said. I can represent G by sigma 3 and X by sigma 1 plus I sigma 2.
Yes, that's right. But not a single
I
one.
mean, if you change the sign of G, then those are the two representations.
Yes, so yes, you're right. By a combination, but not like a single one.
I'm completely lost. Where is this connected to? So this algebra is realized, so there's a Z2 times Z2 is realized projectively.
So, well,
What does the minus sign mean?
the minus sign here.
Yeah.
It's just sorry. No, it's just I'm just defining for you the algebra
The algebra.
called T4. This is just the algebra as an associative algebra. It just satisfies these rules. What I'm telling you right now is that these are the objects inside the representation category. There's something called projective objects. Don't confuse that with projective representation. But yes, sorry about that. It comes from projective object as a projective kind of module from like that type of like module theory. But you should really just think of them, in a nice category like rep S3 or something like that. I just have these objects, right? They're just called names. This is the same idea, except this guy is just a little bit more fancy, right? It's a basis of two elements and it represents this associative algebra. And this one also does as well. So these are the four guys that are going to be important for our story.
So if I try to connect it to, at some point you said there should be a symmetry of something.
That's right.
Should I think of the something as being some Hilbert space that I act on?
That's right, exactly.
Will these X and G be operators acting on that Hilbert space?
So what I'll say is that I'll construct a Hamiltonian that's symmetric with respect to this category.
But symmetric with respect to category means that has Z2 times Z2 symmetry, or will it mean more because of the minus sign?
This Hamiltonian has all the symmetries of this one. So in particular, it has kind of like a Z2 symmetry, but it has even more symmetries.
Nadi, where are you getting the Z2 times Z2?
One generated by X, so if.
This is not a
No,
Z2.
X
That's a zero.
Zero. That's a zero. That's not a Z2 symmetry. There's only one Z2 inside here.
So what's the role of X? It's not a symmetry operator.
It's X is part of the algebra, right? The symmetry operators are really these guys coming from the category. You'll kind of see the role of the nilpotents later. But this is sort of going back to Yichu's question. The fact that this is nilpotent leads to these projective guys, because as Greg says, I can't split this guy back. So these objects are more interesting than the fusion objects. This is not a sum of these guys, but as I'm about to write down, you can have sequences. You can have an exact sequence S0 going to P1, going to S1, and there's another sequence S1 goes to P0, goes to S0. But these sequences don't split. So P1 is not a sum of these guys, and P0 is not a sum of these guys.
Construct symmetries which are labeled by representation of that algebra instead of that element of the algebra, right?
Exactly, representation of that. The categorical symmetry is basically, it's this
The
category.
operator would be, the non-invariable symmetry operator labeled by representation.
That's right. It's the same sort of thing that people talk about, like rep S3 or something like that. It's really this categorical symmetry that's playing the role, not the algebra. The algebra is just generating for you these types of symmetries. But of course, there are certain lattice systems and things like that have a Hopf algebra symmetry. This is in particular an associative algebra, but I can make it into a Hopf algebra. And people have constructed certain lattice systems in 1+1 dimensions with just a Hopf algebra symmetry. I'm constructing something with rep of a Hopf algebra symmetry, which is a categorical symmetry.
Yeah, I don't know what your physical application is going to be, but I'll just comment that this kind of thing happens all the time in quiver representation.
Absolutely, exactly.
Okay.
Yeah, so someone like you, you're someone like you,
Comes
right?
up in BPS states.
That's right. Someone like you would be like, of course, non-semisimal things are interesting. Twisted kind of gauge theories and things like that as well. It's very ubiquitous. Now, if you're like a W algebra theorist, there's kind of a problem there, which is that you have like these infinitely many and even families of like operators. I have no idea what to do about that. I'm in a finite case. Okay, so this is all the math that will actually no, this is not all the math. There's a little bit more that I need. Am I going too slow? So in the case of fusion category symmetries, in the fusion case, in the fusion case where I consider a category C that's fusion, the symmetric gap phases from gap like labeled by the indecomposable module categories. And so in this spirit, I want to kind of investigate what happens when C is non-semi-simple. So I'll have to look for what we're going to look for, kind of look for module categories of C, kind of maybe of B, where B is not semi-simple, particularly B is equal to that guy. But now the module categories here, they no longer have to be semi-simple module categories. These categories usually, usually you consider semi-simple module categories, but here, look for module categories of C, kind of B is not semi-simple, B is not semi-simple, but kind of mod B need not be semi-simple. Right? So what am I trying to say? I'm trying to say that kind of there's two types of boundary conditions you can look for. They're both going to be interesting. And what I need to do is I need to describe the module categories of this thing. And I can describe the module categories basically by looking at them. So algebras. So this is the fact that ostrich that module categories correspond to algebras inside. Using this fact. So, it is a fact that the module cats of mod T4 correspond to lat T4 full module algebras. Okay, whatever the heck that is, doesn't really matter. The details don't actually matter. I just want to label for you the two algebras that are actually interesting because they're going to correspond to the ground states that we're going to see. So here's an algebra. And I'll spell out for you what this looks like. It's generated by y such that y squared is equal to c, and c is just an invertible complex number. Okay. And since it's in particular a co-module algebra, there's coaction of this. Okay. And another algebra that I can consider, which is this thing, y, but now y squared is equal to 0. So I really want to separate out kind of the cases. You can think of this as kind of c is equal to 0. The weird thing here is that is that kind of what you want to construct from this is you want to construct modules inside this category. Let me call this C of this algebra. And this is nice. So it's just going to S0. The object inside this module category is this is a semi-simple module category. And this guy. This has objects which I'll call S and P. And P has a map to S, there's a map from S inside here. This is a non-semisimple.
Is it right down the fusion or multiple?
Yes, so the fusion rules. Yeah, I'll do that in a second. Let me just make a quick remark here. So what am I trying to say? I'm trying to say that given this symmetry, I look at the module categories. The module categories fall into two types of things. There's our semi-simple classes and non-semi-simple classes, and we're going to see that they both give kind of interesting physics. Let me make a quick remark about this one.
So the module categories of T4
Of T4.
are the module categories of these two algebras.
That's right. This is a module category, right? Because it's a module category C with respect to some algebra.
Oh, wait a second. So that, yeah, I mean, you wrote, wait, I'm confused because you said it's co-module.
So that's right. So there's two ways of constructing this. It turns out that using co-module algebras gives you also, this is a theorem that you can classify the module categories by looking at kind of co-module algebras. So this is just, I'm just listing for you the possible types of modules for
I
C.
think I don't understand the notation. You have modules of C, but
Yeah.
is C the
C is this guy, sorry.
I'm really lost. You're looking at the module categories of some tensor category.
Of some tensor category, that's right.
The tensor category.
The tensor
is
category
what? It's
is-
the module, just the module category of the Taft algebra.
It's
right?
So it's the module categories of the category, right? It's the category of ways that this category can act. It's the category that has an action license.
I thought you were gonna write a tensor category and then study its module categories.
Yes, that's right.
So
This
the
is the
tensor
tensor category.
category is the category of modules of T4.
That's right. And I want the modules of this tensor category.
Good, I understand that.
Yes.
And now
And
you're saying you can identify that. I'm not quite sure I understand the notation. Mod sub C of A. A is an algebra.
yeah, so I'm just saying that there's different ways of extracting a module category from C.
Okay.
There's two types of module categories.
Okay.
There's one family. It's really a family because of this parameter, right? And there's another type, which is just kind of this parameter set at 0.
So I see. So one has the objects parameterized by a complex, non-zero complex number.
Yes.
And the other
Just that guy.
is has this one object.
So it's the identity and kind of the
No,
non-trivial.
the other one, the case psi equals 0.
Oh, that's right. So you have a simple object and a projective
Okay,
object.
two objects.
Yeah, and then there's a sequence that looks like this.
Okay.
And I really want to make a distinction. So this is a very important remark, which is that in the semi-simple case, you also have deformations of module categories, but these deformations happen to always be trivial. It's the statement of Oppian rigidity. This is not the case. In particular, it's not Morita to mod C of A1 C prime if C doesn't equal C. So these are genuinely different module categories, depending on the parameter. And what we'll see is that we can construct kind of ground states where kind of you could distinguish the fact that you're living in one of these or one of these. So it gives you like another parameter to work with. And this is a thing that you can see in kind of the physical Hamiltonian that I'm about to get to. This one has other interesting physics as well. So yeah, just to summarize, these are the two mathematically interesting facts about this category. There's semi-simple phenomenon, which means that kind of you have a family of semi-simple ground states, and the ground states are all not related to each other, depending on what parameter you choose. And then there's another type of ground state where this is set at 0, but this corresponds to states that are sort of non-semi-simple. And now I'm about to tell you like the lattice model that has this.
You didn't tell us why mod T4 is a tensor category. Do you have some kind of extra structure on that algebra, like co-multiplication or something?
That's right.
Or is it a hot problem?
That's right. It's a hop algebra in
It's a
particular.
half algebra.
Yeah, I didn't tell you the hop algebra rules, but you don't need them. But yes, it is.
So it's a non-semi-simple half algebra?
Yes. So to put on my promise, So this looks like rep C2. And then P1 times tensor. So let's say Pi tensor Pj is equal to P1 plus P0, P0 plus P1. Projective objects are always idealizing inside this category. So you take an object, take a projective object, it always leads you into the projective objects. So S times this one is, so S1 times Pi is going to give you kind of the other one. So P1 is equal to P0, S1 times P0 is going to give you P1. And those are all the ones that you need.
I and J can be any 0 or 1.
That's right. And any 0 or 1. Okay.
S0 is the identity.
S0 is the identity object.
Is the condition 2 here is something non-trivial or not?
Condition 2 we won't need. I just put it there for completeness. But indeed, actually, this is a interesting phenomenon about Karuba completion. So I'll make a remark, even though we don't need it for this talk. There are certain ways of constructing higher fusion categories through Karuba completion, but there's no guarantee that this procedure of kind of de-looping your category and Karuba completing necessarily lands you in the world of semi-simple categories. Like you can imagine something goes wrong when you go with like higher category numbers. This is something that kind of Theo Johnson, Fried, and I have like talked about at length. So you might worry that this. So just as a remark, this Karuba completion procedure for constructing higher fusion categories may actually fail to present you a fusion category at some category level. For today, we don't care about them at all.
So here, the non-semisimplicity coming from the fact that P0 and P1
Are not direct sums of simple objects.
right? So they are not simple in the sense that their harms is not.
That's right. And you can have harms in there labeled by those exact sequences. And yeah, and you have simple objects, yet this is not a direct sum of simple objects. This is sort of going to what a projective module means in general. Any further questions?
So P0 is simple or not?
The P's are all projectors, so they're not simple. Projective object just means they're not a simple object. And it's not a sum of simple objects. That's what it means to be projective. It's just matters.
Are there endomorphism?
Sorry.
What's the endomorphism of P0?
So P0 is actually interesting. So here's how you should read this diagram. There's a map from P0 to S0. There's a map from P0 to S1, right? Because you go here.
P0 to P1 or S1?
P0 to P1 passing through S0. But this sequence is exact. So you can't go further more. So you can't go back to P0 again through this sequence. That's how you read that, all the endomorphisms. Remember, a category is interesting not because of its object, but because of the morphisms. And these categories have interesting morphisms.
So I'm just asking about home P0, comma P0.
Yeah, that's true.
Oh, that's 0.
That's true. But there's a harm from here to here, which passes through here. You can see it's 0 because there's no way for me to go back, right? It's exact. You can read all the harms from this diagram.
So the endomorphism of both P0 and P1 is just C?
Yeah.
So would you call them simple or not? I thought that simple means.
It's 0.
Yes, 0. Sorry, it's 0. My bad, it's 0.
Oh, there is not even identity morphism from P0 to itself.
No. It just is 0. Like if you go in the sequence, it just hits 0 because two elements of the exact which just kills it.
That's why it's not simple.
That's why, exactly. And you see this sort of the non-semi-simple spread. It's like some sort of nilpotence thing showing up due to the fact that atoms.
Now you got to really confused. What's home P1, P0, P0?
It's 0. Just the 0 math.
But you always have to have the identity in a category. If you have a hom of an object to itself, that's part of the definition of a category, that the identity morphism is there.
The identity morphism is. No, you're right.
Category has the property that there's an identity morphism.
Yes, Greg is completely correct.
Let's see.
So harm of P0, 0 is equal to C.
But that definition of a simple object
No, it's part of the definition.
is not enough.
We said we were equivalent conditions now, yeah. Oops.
Right? It's not because of S1.
I think. Sorry. This actually is the 2 dimensions. It's a 2-dimensional space. That's right. There you go. Thank you.
Now we're talking.
Yeah. It's a 2-dimensional. These are 2-dimensional guys, right?
Yeah, and yet it's indecomposable.
And yeah, it's. Thank you. It's really hot in here. Let me erase. So, okay, now to the Hamiltonian. I'm gonna write for you a Hamiltonian and then we'll just unpack its symmetries. So let this be a lattice inside Z. I'll take this Hilbert space. The lattice C2. I'll express no C2. 0, 1. Okay. And then let C the element of this, construct the Hamiltonian as a function of this parameter. It's going to be given by here. It's 1. And so I'll write this projector. One half I insert minus where sigma x c is equal to c 0, 1, 1 over c 0 plus is equal to 0, 1, 0, 0 sigma minus is equal to 0, 0, 1, 0. Okay. So some interesting features about this Hamiltonian is that one, it's gapped. But so it's gapped. It has a Z2 symmetry. It's just sort of the product of Pauli Z matrices. But interesting enough, it's sort of it's not a Hermitian. Oh, maybe I'll say one thing first, which is that it has more than just the two. It has mod T4. And sort of because we constructed a Hamiltonian in such a way that it has more than just these symmetries, it turns out that these symmetries make it so that it's actually non-Hermitian. And this is sort of an interesting thing, right? Like mathematically speaking, this category is not going to be any type of unitary category because these morphisms don't go in the other direction. And you can see this already showing up actually. So when you impose these new non-semisimple symmetries, you get these more like kind of non-unitary phenomena due to the fact that you have these morphisms. But it's not Hermitian, but it's sort of something that's called like pseudo-Hermitian. So gives you interesting Hamiltonians like this. And let me give you.
Is it a normal matrix? Or is it a normal operator on the Hilbert space? Does it commute with its adjoint?
Does it commute with its adjoint? I think it does. So
I'm asking if the Hamiltonian itself, Hamiltonian in quotes, has non-trivial Jordan form or not?
Yes, it has non-trivial Jordan form.
The Hamiltonian will have non-trivial Jordan form.
Yeah.
What does pseudo-Hermitian mean?
So pseudo-Hermitian just means that instead of H equaling H star, there's sort of a there's a invertible Hermitian operator such that H star is equal to this.
Is it a commuting projector Hamiltonian?
Yes, this will be a commuting projector Hamiltonian. It's also frustration free. Not conditions that I care about that much, but their properties. Okay, so let me tell you also the ground states, that break the Z2 symmetry. So ground state subspace. This is not a good support space. So subspace.
So it's not diagonalizable, so I'm not even sure about this language ground state. So I mean, it does have some eigenvectors and you're looking at the spectrum of those eigenvectors.
Yeah.
But not a complete set of eigenvectors. Because you said it has a trivial Jordan form. Every complex matrix has an eigenvector, at least one,
Yes,
but maybe only one.
yes.
So, I mean, supposing this, in the extreme case, there's
Yes, so
one eigenvector, that's called out the ground state.
that's right, yeah, that's right.
So,
And then I'll give you the ground state that kind of breaks the Z2, symmetry.
is the ground state energy real?
Yes, these have real eigenvectors. Interesting enough. So plus or minus C. That equal sort of 0 plus or minus C 1. But the interesting point is that you have an S1 parameter family. And then now sort of I'll spell out a little bit of the details of like how you can get the mod T4 symmetry. The way you do it is exactly how Tom was kind of expressing it, is that if I have sort of this lattice, then there are sort of certain operators that I can construct. W B0 is equal to sum of some labels. E1, E2, 1. This is a little bit more detail than I really need. One, two. And so the point is that we have to choose these objects. So we choose these guys where, I should tell you the label. So D1, D2 can be 0, 1, and then B1, B2, B0, 1. So we have 4 of these guys. And the point is that I have to be able to kind of choose these labels 0, 1, 0, 1. I choose these to be like certain matrices that are going to reflect the symmetry. So particularly this guy is going to be like this guy is going to be Z, this guy's going to be 0. So the way that you test these symmetry operators is sort of like there's a way acting by the symmetry operator, which looks like this. Your system. I should also say that this. So yeah, I should say this gives you a symmetry operator, and then the Hamiltonian is sort of commuting with the symmetry operator. So you can kind of act by the symmetry operator and then act by that Hamiltonian, or you can act by the Hamiltonian and the symmetry operator, and using some moves that you have, kind of using some of the moves guaranteed for you. So you kind of do this. You can take this guy and you can kind of basically move this. And then you can collapse all of these bubbles.
So can you explain the ground state? What's the ground space? I cannot read that. So it's C to the power of n.
Oh, sorry, it's the size of the lattice.
Okay, and what's the right answer?
0 plus or minus C.
One tensor power, I mean, I don't understand the equation either.
What is the
You're missing it.
I'm sorry. This is equal to this, and then the whole thing is sort of a tensor power of one of these things.
So the ground state is unentangled?
Yes.
product state?
Yeah, it's a product of this. That's right. Where each of these ones is equal to this.
There's 2 ground states, the 2-dimensional ground space.
This is a 2-dimensional.
So you don't really need the vertical lines in the NPS.
So these?
No, downstairs, because really it's a product state, but.
Oh yeah, I'm drawing in general because yeah, later on I want to use this a little bit more. So so here's the interesting claim, right? The interesting claim is that because we have this.
So what is sigma x on this state? Or sigma plus and sigma minus?
So it just acts however it would act on like 0 or like 1.
Yeah, but how it acts? What is sigma x on this state?
Yeah, I think so. Yeah, that's right. So this one will take you from the plus to the minus.
Sigma x, I see.
Yeah, sigma x. So kind of intuition here. Is that the two states represent simple objects. The first kind of semi-simple module category. But now what's interesting is that by looking at the associator, what's going to be the non-trivial module associator, we'll actually be able to tell apart. You can like really tell apart the ground states are different. I'll get there in a bit. Values. So I'll define. I don't know who asked that question. I'll define the module associator in just a bit. The idea is that the module associator is sort of, this is how you should think about it. You have a symmetry action, right? And I can try to act again by the symmetry operator. And then there's kind of an associative action of kind of two actions of the symmetry operator. You can act this and act that, or you can act by the two symmetry operators and then act there. And then by looking at the non-triviality of this, you can actually tell apart the two different ground states for different values of the C, which is the really interesting part. So I'll spell a little bit about that. I'll spell out a little bit about that just coming up.
So in this classification of module categories, are we missing the regular module?
Oh, that's right. That's right. So of course, this is a module over itself. I don't care about that for right now. I just want to tell you these two.
Other than that, these are.
That's right. In fact, there's a label here which is 1. There's also another label called 2, and then that one kind of gives you the same thing. But
doesn't come with a value.
yeah, those are semi-simple, but it's not so interesting. Yeah.
Are these older modules? Does it have a one-dimensional module?
So
Well, you said it has a
Right,
fiber
yes,
function.
yes.
yeah, that's right. It has a fiber function. So it definitely has, yeah, not. Okay, so right. So I want to tell you a little bit about this, about the association. For instance, that if I have two actions of this neutral, then we have the following, then there are following equivalences. Which is so you can have kind of this one, you can write it as sorry. Sum over series. Sorry. Let me just write this down. The point is that this is going to be equal to a sum. You have a sum here. There's lots of labels that maybe I'll just ignore for the moment, unless you guys really want me to spell it out. And then there's actions the symmetry operator of this. So this is exactly, so the symmetry operators, I should say, come with a couple more properties, which is that you can kind of fuse these two together. So by acting them first, you get this type of thing where you can take this one and kind of write it as this type of object. And then here you kind of bend these one down, and then you get something like this, and then you get something like this. If I just focus on the right half of this diagram, this is the F symbol, right? So let me actually write down some symbols so that we can actually get a formula to work with. Let's call this phi 1 alpha 2. So this 1 alpha 2, 3, and then 3, 2. This is going to be equal to a sum over gamma 3's. So 0, 1 of F symbol 1, 2, 3. So these F symbols are not unique. You can perform kind of gauge transformations on these F symbols. You can kind of write this F symbol. 1, 2, 2, 3, 2. And there's sort of these U symbols, which are, and U is just really a complex number that's really fixing these phases, or kind of you can act on these junctions, and these degrees of freedom allow you to really modify this F symbol by U1 factors. So all these U's are elements of this one's inverse. It is whatever it is, but very interestingly enough, these F symbols fall into different equivalence classes. And what you can kind of show is that if you plug in values of these guys, you kind of fix them for a specific value of C. You can try to use these gauge redundancies to see, oh, is there a way for kind of me to implement a gauge transformation to go from one type of F symbols to another type of F symbols, where the other type of F symbols uses a different value of C. It turns out you cannot do this in a consistent way with respect to all the F symbols. So you're going to mess up some of the other F symbols if you try to shift some other F symbols. Which really tells you, and this is a very explicit way of realizing that fact that they're not Morita equivalent, is by looking at this associator. And this is just a tough computation that we had to do. There's theoretical ways that you can also prove this, but it's very down to earth. You just analyze the associator, you look at all these symbols, and you see that manifestly there are certain symbols that if you fix to a certain value, you cannot, like, you basically can't change even with gauge transformation. So really just for that, for that thing. And I could do the computation, but let's not focus on that here. So much for the first example. Now, for the last part of the talk, I just want to focus on these types of ground states. And this is really so one feature of the non-semisimplicity is the fact that I have this family. We already see the implication of this family. I want to show you the implications of this guy now.
Can I just ask one more? So with this family, they are due to breaking, but they preserve non-invertible symmetry.
In what sense? Yes.
That by non-invertible symmetry NPO, then is the ground state invariant or?
Yeah, it breaks the Z2. But you're asking about the other.
Yeah.
Not T4 symmetries.
Right.
I think they are. Yeah. In fact, they have to be, because I can kind of this is essentially this argument, right? Is I'm using the other operators here to be able to tell apart these two states.
Non-invertible operators are preserved.
Yeah. If you want to say it that way, that's right. It breaks part of them and leaves some of the other ones. Is that what you're trying to say?
Yes.
What's the ground state and maybe it's a function of psi?
I don't remember.
Just wondering if that would distinguish the.
It's interesting. Well, I guess it's interesting that this symmetry can also distinguish the different types of ground states, the non-invertible symmetry.
I'm just wondering if the ground state energy already.
Yeah, but to go along with the moral of the story is that this is interesting symmetry that has some consequences. So let me get to the part that I think is also very interesting.
Does the finite temperature partition function exist? Trace of eta minus beta h.
I didn't think about that. I don't know.
Because H is non-trivial Jordan form, so.
Yeah, maybe I'll just say we didn't look at that. Okay, so
Yeah.
the case of C equals to 0, so now we have H0 minus F+1 so it still has so this is the thing, and then such a Hamiltonian. H0 has the mod for symmetry along with some of the other nice properties that I listed above. But now the ground states, are interesting. So they're spanned by, so now the ground states are
I'm
going
having a little problem in psi equals 0 in your formulas.
yeah, that's right. It's
Psi has a 1 over the square root.
yeah, exactly. It's not,
It has a 1 over the square root of psi, but you only have one factor of square root of psi outside.
yeah, it's not,
Infinity.
it's not a continuation.
Okay.
As I said, it's really two different things. I don't want you to think of it as a continuation. It's just a different type. Ground states. So first, I just have this product state, and then I have this state that I recently learned about called the W state. What this is sort of kind of it's like 0, 0, 0, 0, 0, and then 1, and then plus like 0, 0, 1, 0, etc., etc. So it's like this type of thing. I should mention that there's lots of people have been studying these types of W states and things like that. It shows up in quantum information quite a lot. It shows up here. It's non-invertible symmetry. So to parallel as before, so kind of parallel these two states, you should think of as coming from objects of the other type. And so why should you think of it in such a way? It turns out that actually thinking of these two states in terms of kind of this exact sequence and the fact that the product state corresponds to this and the W state corresponds to the projective object leads to some interesting consequences that people have known about the W states, but you can interpret these using this type of categorical symmetry. So I'll end with a couple of remarks explaining sort of why this is significant. So a couple of remarks. So it was noted by Thorngren and Yang. That the W state not be the single ground state of a local Hamiltonian. In fact, it is accompanied also by this product state. And this is really cool because, as I said, in this category of symmetries, if you look at the module categories, there is a module category that looks like this. You can't have a module category that has only one or other. It turns out that just doesn't exist. So the fact that the boundary category really looks like this and has these two objects really is a nice reflection of like this fact that these two have found. It's really the fact that the module category has two objects, and you can't really separate them. Otherwise, it's not a valid module category. The second thing, the second remarkable is that the W and product are indistinguishable in the infinite volume limit. This is a result of Nijkens. And sort of this fact is made possible for us by the map that goes P to S, and also the map that's going in the other direction. So the fact that these two states are really indistinguishable, well, we have these maps, we can always use these maps between the objects. So now this really tells us that kind of you would expect that they are actually related to each other. This is a nice thing that you see from the non-semisimple setup. The third thing, which I would just harp on a little bit, I didn't really go into that much into this already. This is just another fact. So the third thing is the W state cannot be parameterized as a translationally invariant tensor state.
Does this math between P and S means a massless domain rule between the two states?
I think my physical interpretation of that one is not necessarily so clear. Just the fact, yeah.
Usually I would think that there is a morphism between, but there are two states or two boundary conditions. A morphism is just an interpolation between the two. I would think that you have some states which on the left it looks like 0, on the right it looks like a W. You have a domain wall, and probably it has a
Sort of on the, in terms of the lattice construction, you can indeed think of it this way. You can think of it as there's a morphism that happens like kind of on the chain that goes between S and P or P and S.
Yeah, but I think the surprising fact here would be that it has kind of maybe like a zero energy.
Okay, that, I mean,
is that true?
I never actually thought about it like this. I actually don't know. I think that's maybe an open question that I'm actually not sure of. I could say that kind of you could ask this question again for other types of categories, but maybe it's not so interesting. I'll have to say that the fact that we saw the W state come out of this example is kind of a surprising fact. You know, there's other types of categories whose module categories has lots of objects, but no guarantee that those states will also be related to each other. Maybe it's true, but maybe it's not. I haven't seen all those examples, so I don't necessarily know if your fact applies to all cases. Okay, so it cannot be parameterized as a translator invariant tensor network state with sort of periodic boundary conditions. And it turns out that in constructing constructing the lattice model for symmetry, we also had to take this is not something that I really talk much about, but it's actually true. You need to do this in order for the symmetry to act faithfully. So it kind of aligns with this interesting fact that you have to put it in, you can't put it on closed boundary conditions. So those are the three interesting things. I've gone through the talk. I think I can stop here. Thank you guys for listening.
So for the last point, what happens to the model with periodic boundary condition? I mean, you sacrifice the symmetry, but you can study this model.
You sacrifice the symmetry, but you don't get all the symmetry operators that you would have in this category.
How about the ground state? Ground state is just completely different.
Yeah, if you do that, then so if you do such a thing to the ground states, the thing is that you want to build a ground state in such a way, right? You pick the open boundary, you pick, let's say, periodic boundary conditions on both sides. What turns out, if you try to study the symmetry now whatever ground state you have with the non-periodic boundary conditions, it doesn't have all the symmetries. My premise was that I always want something with a certain amount of symmetry, so I need to fix the condition so that it reflects all of the symmetries. That's my premise.
It looks to me like the W state has non-trivial entanglement. Just take two lattice sites, then it's a bell pair.
Yes, that's right.
Okay, so that means, I think it has non-trivial entanglement. So how is it that the W state is indistinguishable from the product state, which has zero entanglement?
That's a good point. In the infinite volume limit is the condition that they have there.
Is there a factor of 1/√n?
I don't know. Let me just take the infinite volume limit and trace out.
For any local observable, its average is going to be the average is going to be the same when n goes to infinity. It's like with conversions.
I guess there are many zeros of only one.
Yeah.
So it's not quite. So the entanglement.
Oh, you're crazy. Well, I just gave an example of two sites when the entanglement is obviously there.
Oh, yeah, 2 sides.
But so I would think that with finite number of sites, there's non-trivial entanglement.
Yeah, I'm making an infinite volume.
Maybe somehow it goes to zero. The volume limit.
Do you think there are any Hermitian Hamiltonians that have this symmetry?
So we tried looking for them. So I think there are none, and I can back that up
I
because
think there are none.
I think you can't have a Hermitian Hamiltonian that has this type of symmetry on it because of these maps. Unitarity is a condition on the morphisms of the category, basically saying that I have a dagger morphism that reverses any morphism, but these I can't reverse.
I see.
So that's how I back it up.
Okay.
And we tried to look.
Any other questions?
If you use this non-semi-simple category and input it to the anionic chain construction, would you recover your lattice model?
Yeah, we actually did it from the anion chain. Yeah.
Oh, that's how you construct.
Yeah, that's how I didn't want to get into the details too much about it, but yes.
So is there a way you can get a second order phase transition and somehow by tuning parameters? Where I'm going with the question is would it be related to logarithmic?
So this is a great question. I've thought about this a lot because I got interested in log CFTs when I went to Oxford. I don't think that this is related to any type of log CFT. There are, however, yes, so
Maybe there are other examples.
So you can, of course, ask yourself, take the representation category of a log CFT and see if I can construct a thing with that type of thing. I have not tried that such a thing. It's kind of difficult, but one thing you could do, a log CFT that you might like a lot is the triplet algebra. The representation of category of that thing is actually finite. It's kind of Morita equivalent to the singlet algebra, but it's also Morita equivalent to the singlet. It's called the singlet W algebra, like the singlet. Anyways, it's called the triplet because inside the VOA there's the stress energy tensor and there's two W currents, W plus W minus, whereas the singlet only has like a single W. The representation category for the singlet is wild. The triplet is not so bad. It turns out it's actually a finite thing. So you could try to build a model with sort of rep of the trip. Rep of the singlet is sort of like the wild west of like category theory. Really, it's super nasty and like you have a continuous parameter. It kind of looks like this, but there's parameters now of like simple objects and at certain parameters it ends up being projected. So it's really crazy. I don't think this
Formal
will,
field theories, usually we think of them as coming from second order phase transitions of lattice systems. So I'm trying to connect.
so,
what I
so.
think you're talking about.
So I think such a thing might be possible if you can find a Morita equivalence between this category and another category, which is the representation category of the log CFT.
Is there any more questions? Thank you, Mr. Again.